Hi everyone, my name is Sam Go and I am joined by my brother Josh Go. In this module, we will be going over 40 sample questions that we picked from previous geometry regions, and the types of questions that we chose are according to the breakdown provided by the Regents board. The breakdown is as follows. For congruence questions, 30% or 12 questions. Similarity, triangles, and trigonometry at 30%, another 12 questions. For circles, 5%, 2 questions. Geometric properties, 15%, 6 questions. Geometric measurement and dimensions, 5%, 2 questions. And finally, modeling, 15%, 6 questions. So without further ado, let's begin. Question 1. On the set of axes below, pentagon ABCDE is congruent to A double prime, B double prime, C double prime, D double prime, E double prime. Okay? Which describes a sequence of rigid motions that maps ABCDE onto this second pentagon, right? So let's just be clear about which one is which. It's very easy to do the question and do it incorrectly from the get-go. So this we'll call A, okay, we'll call this one B. So we're gonna go from A, that's this guy, to this guy, okay? So let's see which one's the correct answer here. A rotation of 90 degrees counterclockwise from the origin, followed by a reflection over the x-axis. That starts to look a little promising when we rotate this first pentagon over the origin 90 degrees counterclockwise. We'll get something that looks like the second pentagon, that same shape, but it's going to be somewhere up here. The problem with it is when we do that rotation, and this is not to scale, these will be the coordinates, okay? We're going to have A, B, C, D, E, just like this, right, when we rotate it. The problem with this is when we reflect it over the x-axis, okay, when we reflect it over the x-axis, A would be here, okay? So that is incorrect. It would not provide a correct mapping. So let's try choice 2. Choice 2. I'm going to erase the work for choice 1, all right? A rotation of 90 degrees counterclockwise about the origin, so same idea here. So here's our, here's point A. I'll do this to scale. Here's point E, okay? Here's point D. Here's point B, and here is point C, right in the middle, right here, okay? So now it's saying we're going to do that same rotation as we did in answer choice 1, but we're now going to translate it 7 units down. So this one will go 1, 2, 3, 4, 5, 6, 7. So that goes to A, so that's good. And if you look at it, all the shapes, because it's a rigid motion, will translate to their corresponding letter. Okay, so we could be pretty confident here that choice 2 is the answer. All right, next question. Which transformation carries the parallelogram below onto itself? Basically, which one of these transformations would allow us to see the same parallelogram that we're seeing here right now? Okay, so let's entertain these first two options here. They look very similar. Reflection over y equals x. Let me just draw that line. That's approximately this line here. We're reflecting. And reflection over y equals negative x. That's approximately this line over here. So there's a couple formulas if you want to use them. You don't have to. You could kind of do it by kind of eyeballing it as well. But if you're reflecting over y equals x, okay, the point xy, the original coordinates xy, transforms into yx. You just flip them, right? So let's take this point, for instance. That will become right over here, right? We're reflecting it over that line. So this will be 3, 4. That is already not on the original parallelogram. We can eliminate that answer. We don't have to do the other points. Let's do y equals negative x. Okay, what does that do? That takes our original coordinates xy and transforms it to negative y, negative x, right? So we'll take now, let's try to take point M here. Okay, let's take point M. Negative y, negative x. So that would put us at negative 3, positive 2. That's about here. Just gonna kind of bring it over here, right? Negative 3, positive 2. That is also not on the parallelogram. We can just eliminate that as well. That's very convenient. For the next option, a rotation of 90 degrees counterclockwise about the origin. So what we can actually do is we can use the formula if we wanted to, okay? So rotation would give us these coordinates, a rotation of 90 degrees. I'm going to use a blue color here. Rotation about the origin, okay? So rotation of 90 degrees counterclockwise about the origin. We'll say that, about the origin. Would take our points x, y and translate them, or map them into negative y, x. We can see what that looks like, okay? Let's take point t this time, okay? Take point t. So t is originally 2, negative 3. That will change to t, we'll call it t prime for the translated one, the mapped one. That will be negative 3, so that's positive 3 and 2. Okay, so let's do that real quick. 3, 2, that's about here, right? When you rotate it up, kind of comes around to here. So here's also, you don't have to do this for everything. You can tell already that's not going to be on the parallelogram, but the current parallelogram looks like this. And if you kind of turn your head to the side and that 90 degrees, you will actually find that the next parallelogram, when it's transformed, doesn't even look the same, right? So if we did do the rotation, I'm going to do this in a different color now, it would look kind of like this. Okay, so it would be completely, it's kind of pointing in the wrong direction, right? The parallel sides are now pointing up. Or sorry, the sides that were parallel to the x-axis here, right, are now pointing up. So that's definitely not going to be that either, right? So we can be confident 180 degrees rotation would do this, would give us the same parallelogram, because you can imagine if you turn your head one more time for that, you'll come right back to the original parallelogram. All right. On the set of axes below, triangle ABC is congruent, that's that symbol, congruent to DEF. Okay. Describe a sequence of rigid motions that maps ABC onto DEF. So again, remember this congruency statement here means A will match with A, B will match with E, and C will match with F, right? So there's a couple ways you can do this. There's no hard and fast rule to do this, okay? Here's how I saw it first, okay? So I thought, hey, this is currently flipped the wrong way. I could rotate it 180 degrees first, about the origin, okay? So let's figure out where that goes. So I know right here, this point A is negative 3, positive 3. If I rotate that 180 degrees, it will go here, and then it will go here, right? And you can use formulas to do this, of course, but A would now be here. I could just draw the rest of the triangle because I can eyeball everything and say, okay, well, there's B, that's 3 units, so that goes down 3 units. And then there's C, goes over 4 units from point B. So now we got a triangle. So that looks pretty good already, and you guys could probably guess the next step, I'll do it in green here, is simply to translate this up 4 units, right? So a complete and accurate answer to this would just be to say a rotation of 180 degrees about the origin, okay? So that's step 1. And then step 2 is to translate or translate up, okay? That's plus 4 units, okay? So those 2 steps would be valid. Another way to do this, and I won't go into this too much, but you could actually put point A, I'll do this in blue here, you could put point A first onto point D just by translating over to the right and down, and then rotating the triangle about that point, right? Because essentially you'll have a triangle that you'll have them look like this. A, ABC, D, E, F, and you can just kind of swing this guy around this point. But these two, very fast way to do it. All right, on the set of axes below, ABC has the vertices, and you see them here, and DEF has those vertices. Which transformations will map ABC onto DEF? Now, a couple things here, okay? A dilation, as you see in all of the choices, dilation, simply means you're taking the x and y values and you're scaling them up by some certain number, okay? Now, here's the problem. There's a lot of choices to go through, there's a lot of numbers to work out, but maybe we don't need to do any of these numbers at all. This is what I mean. We know we're trying to map ABC to DEF. Here's ABC, here's this small triangle ABC, and there's this big one here, DEF, okay? That clearly got bigger. ABC has to scale bigger or dilate bigger to get to DEF. So we know that the dilation factor cannot be 1/2. That would make the triangle even smaller. That's not what we want, right? So we can immediately take out choices 2 and 3. Finally, the thing that's kind of distinguishes these two is that this one has a rotation of 180 and this one doesn't. If you scale ABC by 2, it will simply look like this, bigger, right? And you can very easily tell that that's not pointing in the same direction as DEF. It needs to be flipped 180 to look more like this, right? So that's 180 degrees. And just from that reasoning, we don't even have to do the math. We know it is choice 3. Okay, so in triangle ABC, BD is the perpendicular bisector of ADC. Based on this information, which statements below can be proven? Let's talk about a perpendicular bisector. That means it's perpendicular to the side it is bisecting, and the definition of bisecting means it splits it cleanly in half, right? So I'm going to draw a triangle, okay, and this triangle ABC. And it looks equilateral right now. It might not be. It might not be. It could be skinny like this. It could be skinnier. It could look more scalene. We're not sure yet. But let's run with the one I have labeled here. A perpendicular bisector, BD, is dropped from here. Okay, so that's perpendicular, and it bisects, which means these two are the same length. Okay, so we can figure out a couple things here. If they're the same length, if these two are the same length, okay, that means this angle here is also the same. I'll do it with 2 tick marks, right? And if those two are the same, and then they each have a 90-degree angle, so they have this angle here, they have the 90-degree angle here, this third angle also has to be congruent, okay, for both sides. So those tick marks represent which things would be congruent. So let's see which choices are true. BD is a median. Well, by definition, okay, a median is simply a segment that goes to the midpoint of the opposite side, right? And that's exactly what BD does. It hits the midpoint of AC. Okay, so choice 1 is okay. That already eliminates choice 3. Okay. Statement 2 says BD bisects angle ABC. Well, as we said here, I'm going to circle in green now. As we said over here, they're congruent. These two are split cleanly in half. So that is also correct. Choice 2 is also correct. So we're eliminating 2 here. Sorry, statement 2 is also correct. We can eliminate choice 2 because it doesn't have statement 2 inside. Finally, triangle ABC is isosceles. I can believe that, right? We can say this angle here and this angle are, as we found out, they are congruent. That tells us 2 angles of a triangle are the same, is the definition of an isosceles triangle. So choice 3 is also correct. We can choose choice 4. The diagram below shows parallelogram ABCD with diagonals AC and BD intersecting at E. What additional information is sufficient to prove that the parallelogram ABCD is also a rhombus? Just to be clear what a rhombus is, right? It's this parallelogram, so this side here is parallel to this side, and this side is parallel to this side, right? It means these sides are also all equal in length, okay? What we should know, very simple tip to know about rhombuses, okay, is if we draw these diagonals, a very special property of them is that they are perpendicular. They form right angles. With that information, our eyes go straight to choice 4. AC is perpendicular to BD. Just that alone tells us that this will be a rhombus. Okay, in the diagram below, right triangle PQR is transformed by a sequence of rigid motions that maps it onto the triangle NML. Write a set of three congruency statements that would show ASA congruency for these triangles. Let's just remember what ASA means. That's angle, side, angle. So very easily, this will be our first statement, second statement, third statement, okay? It's not very, it leaves it kind of ambiguous which specific angle, side, or angle we can use, but we still have to use it correctly, right? So why don't we say this? Let's start with angle Q and angle M. That's a pretty easy one. So statement 1, we'll say angle Q is congruent to angle M. Okay, so that's our first statement, angle. Let's do a side. Angle, side, angle. Let's do the side here, right here. These two should be the same, right? QP, we'll say QP. So that segment QP is forming that side or that leg of that right triangle, that right triangle, should be congruent to MN. Okay? And as a third one, angle, side, angle, the angle we use will be this one because we're using, first angle was here, second angle is here. We want to use the side that was sandwiched between, so we're going to have to use this angle here, angle P. Not a problem, we'll just say angle P is congruent to angle N. And just with those three statements, you can prove by ASA that these two triangles are congruent. Awesome. Next question here. Given triangle ABC with angle B 62 degrees and side AC extended to D as shown below, which value of x makes AB congruent to CB? Let's just think about what that means again. What value of x makes AB congruent to CB? Here's AB over here, okay, and here's CB. If those two will be congruent, okay, that is the definition of an isosceles triangle, meaning the angles across them will also be the same, right? So why don't we do that first? I'm going to call this y and y, two angles here. We know that a triangle, the sum of the angles in a triangle equal 180. So why don't we do that? 180 equals 62 plus y plus y. That's pretty simple. We're looking only inside the triangle. 180 equals 62 plus 2y. And when we solve for y here, we'll get 59. Okay, and you can check that. So if we now know, we're going to redraw the diagram here real quick. If we now know this is 59 and so is this, and this is 62, we're wondering what this is. Well, I hope you guys can see this is a 180-degree angle, right? We're basically finding the supplement of 59. So we're really just doing 180, right? 180 minus 59 degrees, okay? And that should get us the answer choice, or the number 121 degrees, and that is answer choice 4. All right, question 9. Which figure always has exactly 4 lines of reflections that map the figure onto itself? So this one doesn't really require math, it really just requires us to have a good understanding and intuition, and a good grasp on just all these different geometrical shapes that that you guys will cover in your geometry class, right? So you have square, rectangle, octagon, and equilateral triangle. So let's do a square real quick. Here's a square, equal sides, right? Same length. Does it have 4 lines of symmetry? Let's find out. Here's one, right? Sorry about that last line. If you map, or if you reflect this over that line, still looks like a square, okay? What if we do this line? Still looks like a square. We mustn't forget, so that's 1, that's 2. We mustn't forget there's a diagonal line that goes through that will map it to the same square. And then here's another line, right? So that's 3 and 4. So just like that, we know answer choice 1 is the answer. Let's just see why the other ones might not be. Okay, here's a rectangle. Okay, when you do a rectangle, you will have this same line here, the vertical and horizontal lines. There's a slight snag though that we hit when we try to do this diagonal. Okay, you can't quite do it because this point down here will map to about here. Okay, and then this point will map to about here. So actually we'll get some weird looking shape, and I didn't do this quite to scale, but we'll get some weird looking shape that looks more like this. That's not right, that's not the rectangle, so it's not going to be 2. An octagon, a regular octagon, that means all the sides are the same length. Let's quickly just sketch out one of those. 1, 2, 3, 4, 5, 6, 7, 8, right? It will have 1, 2, 3, 4. But just like the square, you also have the diagonal. So from here to here, that's another line of symmetry, right? That's another line of symmetry. Here's another line, here's another line. So that's actually 8. So it will also not be the regular octagon. And finally, the equilateral triangle, that's same length here. Okay. If you reflect over this line, that's fine. If you reflect over this line, that's fine. And this line, that's fine. But that's only 3, right? So just like that, the answer is choice 1. The graph below shows triangle ABC and its image A double prime, B double prime, C double prime. Describe a sequence of rigid motions which would map ABC onto A double prime, B double prime, and C double prime. Okay, so let's make sure we know what we're doing. Again, first thing, let's make sure we're reading the question. We're looking at this triangle, we'll call this 1, triangle 1, and we're mapping it to triangle 2. So how do you get from here to here? Plenty of ways to do it. The first thing that catches my eye is B. Point B is kind of on the opposite side, if that makes sense, right? This one is to the right side of A, but this one's to the left side. That tells me we're probably going to flip it. Along that y-axis, reflect over the y-axis. So what would that look like? Let's sort of draw that out. I'll do it in blue. So C, we can just count from the y-axis. This translation's for reflection is rather easy to do. Two spaces or 2 units will lead us to here. So this will be C, we'll call it C prime. B, on the other hand, will be way out here, okay? Again, it's just the same distance from the y-axis, like that. And A will be right over here. So we'll have this triangle, okay? From there, we're basically halfway there. We're basically done. You just realize that we're offset by two units, okay? So we just have to shift it down by 2 after that. So that basically means step 1, reflect over the y-axis, okay? And that gives us this one we saw here, this blue triangle. And in step 2, shift or translate down by 2 units. And that will get us that second triangle, A double prime, B double prime, C double prime.
In the diagram below, triangle ABC has coordinates A11, B41, and C45. Graph and label triangle A double prime, B double prime, C double prime, the image of triangle ABC after the translation 5 units to the right and 2 units up, followed by the reflection over the line y equals 0. Now y equals 0 is this line over here. It's just the x-axis. Y equals 0. Alrighty, so we can go about this 2 ways. I'll do them both at the same time. One is to just visually translate it and reflect it. The other way is to use the coordinates they've given us and do the transformations using those. So first things first, let's try physically using the graph, visually moving each one of these points 5 units to the right and 2 units up. So B looks like it's going to end up 1, 2, 3, 4, 5, 1, 2. B looks like it's going to end up here. A looks like it's going to end up here. And C looks like it's going to end up here. And because this is our intermediary triangle, we'll just label it with singular prime, right? A prime, B prime, C prime. Now we can use the coordinates as well. A starts at 1, 1. So shifting 5 units to the right means we add 5 to the x value, right? So 1 plus 5 is 6. It's going to be our A prime. 6, comma, and we're adding 2 to the y value, which it starts at 1. Now we're adding 2. We're getting 3. Let's do the same with B prime. B prime starts at 4, 1. It becomes 9, 3. And C prime starts at 4, 5. And that becomes 9, 7. All right, now let's work on reflecting it over this this y equals 0 x-axis. So I'm going to change colors. So we can just see that because B prime is 3 above this line right now, right? It's 1, 2, 3 above. Let's go 3 below. 1, 2, 3. So this is where B double prime would be. We can do the same to A, drop it down, A double prime, and then same to C. 1, 2. This would be our C double prime. And this would be our final triangle A double prime, B double prime, C double prime. Now let's do this to the coordinates too, just to verify. Now, to reflect it over the x-axis, we negate the y value. So this would turn into 6, -3. And we can verify that by looking at what we've done using the graph. And B double prime would be 9, -3. And C double prime would be 9, -7. Line segment EA is the perpendicular bisector of segment ZT, and ZE and TE are drawn. Which conclusion cannot be proven? So we know that right now we have line segment EA, and it tells us it's a perpendicular bisector. So that means it forms a 90-degree angle with line ZT, and that segments ZA and ZT are identical. So what does this tell us? This tells us that it's an isosceles triangle, because doing this, we know that points Z and point T are equidistant from E. So these are the same. So because it's isosceles, we know that the perpendicular bisector of that line forms 2 equal angles on either side, and therefore this is correct, and therefore we can cross it out. For the second one, we know it's isosceles, but it's not necessarily equilateral. So let's leave this unmarked for now. So unmarked, question mark. Third, EA is the median of triangle EZT. Now the definition of a median is it's a line joining a vertex and the midpoint of the opposite side, basically bisecting the opposite side. So this is exactly what this is. It's a bisector, but more specifically a perpendicular bisector, but it's a bisector of the opposite side. So we can cross that out. It's correct as well. Finally, we have angle Z is congruent to angle T. Now we said it's an isosceles triangle, so we know that these two angles are also identical. Therefore, our answer is 2. All right, so here we start the topic of similarity, right triangles, and trigonometry. So we have the aspect ratio, which is width to height ratio, of a rectangular flat screen television is 16:9. Let's quickly draw that out. Height, it says width to height, so we know the width is 16 and the height is 9. The length of the diagonal of the screen is the television screen size. Determine and state to the nearest inch the screen size of this flat screen television with a screen height of 20.6 inches. So these are just similar triangles, right? Similar right triangles. This one has a height of 20.6, and it's asking us for the diagonal, which is the screen size. Okay, so let's set up a ratio because these are similar. 9/16 equals 20.6 over x. Now x here is our missing leg. We find this missing leg, then we can do Pythagorean Theorem and find this missing hypotenuse, which is the screen size. Alrighty, so in this case, if we cross multiply, we get 36.62 repeating. That's our missing leg. Alright, so then let's just do Pythagorean Theorem. We know that a squared plus b squared equals c squared. And we can square root both sides. A squared plus b squared, square root of that equals c. Now we can plug our two legs into a and b respectively, and then we get c equals 42.018. And then this question asks us to ask for the nearest inch. So we just round that down to 42, and that's our final answer, 42 inches. In this next question, we have, as modeled below, a movie is projected onto a large outdoor screen. The bottom of the 60-foot tall screen is 12 feet off the ground. The projector sits on the ground at a horizontal distance of 75 feet from the screen. Determine and state to the nearest tenth of a degree the measure of theta, the projection angle. All right, so the way we find this angle, theta, is to first find this larger angle of this triangle, and then I guess subtract it from this smaller triangle, right? So let's do that. It seems like we're given the adjacent leg and we're given the opposite leg information, right? So that tells us we're going to be doing tangent calculations. In this case, we're going to be doing an inverse tangent. We're going to find the big angle first. Let's just label that. Big angle. We're going to have tangent, inverse tangent of, now we have SOHCAHTOA, so we have opposite over adjacent. So in this case, opposite would be 60 plus 12, right, of the large triangle. 60 plus 12 over 75, because we're doing this triangle right here. And make sure you're in degrees, because this question asks us to do degrees. Or if you were to do radians, perhaps, then, of course, at the end, convert to degrees. But in this case, we get an angle of 43.83 degrees. And now let's try to find this small angle. So likewise, we do an inverse tangent of opposite, 12. We're doing this one. Let me color it in a different color. Let's go with blue. This triangle. So that would be 12 over 75. Let me put that in the calculator. And that gives us an angle of 9.09 degrees. So simply, we can subtract these two numbers, 43.83. Let's put a few more decimal places on there, just in case. Minus our 9.0902. And then, putting this into our calculator, we get an angle of 34.7405 degrees. But it asks us to round to the nearest tenth of a degree, so this rounds to 34.7 degrees. And that's our final answer. As shown in the diagram below, the angle of elevation from a point on the ground to the top of the tree is 34 degrees. If the point is 20 feet from the base of the tree, what is the height of the tree to the nearest tenth of a foot? Alrighty. So we're given the information that this distance over here is 20 feet. And we're trying to find the height of the tree. Let's make that x. So we know that tangent is opposite over adjacent, right? And in this case, that would be x over 20 would be our tangent. And we're also given the degrees here, so we can just do tangent of 34 degrees, right? Make sure your calculator is in degrees for this one. It could be set to radians, so just make sure and set it accordingly. In this case, we're just doing tangent of 34 degrees. Should yield us x over 20. So to figure out x, we can just multiply 20 on both sides and get 20 tangent of 34 degrees. So doing this, we get x equals 13.490. And it asks us to round to the nearest tenth, and it would be 13.5, which is answer choice 3. David has just finished building his treehouse and still needs to buy a ladder to be attached to the ledge of the treehouse and anchored at a point on the ground, as modeled below. David is standing 1.3 meters from the stilt supporting the treehouse. This is the point on the ground where he has decided to anchor the ladder. The angle of elevation from his eye level to the bottom of the treehouse is 56 degrees. David's eye level is 1.5 meters above the ground. Determine and state the minimum length of the ladder to the nearest tenth of a meter that David will need to buy for his treehouse. So what information are we given? We're given that the base of the ladder is 1.3 meters away, and so is David in this case. I'll model him here with just a stick. And we know that David is 1.5 meters tall. And from his observation, this is 56 degrees. And we're trying to find the length of the ladder here. Okay. So because David is also standing at the base of this ladder, we know that this measurement is also 1.3 meters. Now to find the length of the ladder, we can do a Pythagorean theorem if we have the length of this leg over here, right? Now we have a portion of it, we have this 1.5 meter portion of it right here. And all we have to do is try to find this top portion right here, the length of this top portion. And we can do that with the information we're given. We can do a tangent of our 56 degree angle. And we know tangent is opposite, which is our missing length. Let's put that in x. And then over adjacent, which is 1.3 meters. And just multiplying both sides by 1.3, x equals 1.3 tangent 56 degrees. And putting that in our calculator, we have x equals 1.927 meters. So now we know the length of this top portion. We can add this, let me change colors. We can add this to our 1.5 meters to get this entire leg that we wanted, right? So let's add that to 1.5 to get 3.427. And from here, we can just do Pythagorean theorem, a squared plus b squared equals c squared, with this as a and this as b, let's say. And then we can get c squared, which is our length of the ladder that we were trying to find. Okay, so let's plug it in. Let's first do a square root on both sides, right? Just so we can get c right away. And doing this, we get c equals 3.665. And it tells us to do it to the nearest tenth of a meter, so we can round this value up to 3.7 meters. This question asks, the expression sine of 57 degrees is equal to? So the easiest way to go about doing this question is to know the relationship between sine and cosine. There's a relationship that you should know, which is that the sine of an angle, an acute angle, is equal to the cosine of its complement, meaning 90 minus the angle, right? So in this case, doing that, we get 90 minus 57 to try to find its complement, right? And that equals 33. So the sine of 57 would be equal to the cosine of its complement, which is the cosine of 33, giving us the answer of 2. Now you can also do this manually by inputting each one of these into your calculator, but I feel like putting a significance and highlighting this relationship is important. In the diagram below of right triangle ABC, altitude CD intersects hypotenuse AB at D. The question asks us which equation is always true. Well, to answer that, first we need to find out, to figure out specifically what this altitude means, right? So an altitude actually creates two smaller right triangles, right? Triangle ADC, and creates a smaller triangle DCB, right? And these triangles, all three of these triangles, these two smaller triangles and the big triangle, are all similar to one another. That's an important relationship to know. So which equation is always true? Well, it's whichever answer choice reflects these proportions that we have between these similar triangles, right? So let's quickly look at answer choice 1. Answer choice 1 says AD over AC, so that's AD, this length, over AC, equals CD, this, over BC. Okay? So it looks like it's referring to one leg and one hypotenuse of the smaller triangles that are created from this altitude. So let's see how these how the relationship is to one another, right? Because we want to make sure we're using the right leg. We're comparing the right leg with hypotenuse. So looking at this larger triangle ABC, we know that because angle C is 90 degrees, that angles A and B are complements of one another, right? That being said, this angle, ACD, has to be equal to the angle B, right? Because in this smaller triangle, we also have a 90 degrees, and we also have this angle that we just got, and that means that because in angles A and ACD have to be 90 degrees, that they're complements as well. So that's why angle ACD is equal to angle B. So that also means that this angle, DCB, is equal to angle A. So to visualize that out, it looks like it would be that smaller triangle, right? The smaller triangle here, rotated clockwise 90 degrees so that it would look like that. And I'll draw the larger triangle right behind it. Right? So in this case, we are comparing the correct legs and hypotenuses, right? We're comparing this leg to this hypotenuse, and we're comparing this leg and this hypotenuse, right? So this relationship agrees with these similar triangles. And I'm not going to go over it, but you can see that while going through these other answer choices, that they don't express that same proportion between these similar right triangles. Therefore, our answer choice is 1. Given right triangle ABC with a right angle at C, angle B equals 61 degrees. Given right triangle RST with a right angle at T, angle R equals 29 degrees. Which proportion in relation to triangle ABC and triangle RST is not correct? So let's quickly find out the measure of angle A. Interior angles of a triangle equal 180. 180 minus 90, which is the right angle, minus 61, equals 29. So we know angle A equals 29 degrees. If we do the same thing for triangle RST, we figure out that angle S is 61 degrees. So we know that both of these triangles are similar to one another through angle similarity. Now, just to visualize it better, I'm going to rotate the larger triangle clockwise so that we can visualize the relationships between each one of the sides. So we have A up here, we have C and B. 61 degrees and 29 degrees. Okay. So the question asks us which relation is not correct. So let's look at answer choice 1. We have AB over RS. So AB is this hypotenuse of the larger over hypotenuse of the smaller. AB over RS. So we have big hypotenuse, the big triangle's hypotenuse, over the small triangle's hypotenuse. I'll write that as HYP. So what we're looking for is another, on the other side is something like a big over a small, right? In this case, we get RT, which is a small, over AC, which is the big. So this proportion doesn't follow, right? You can't compare the big to the small and then the small to the big on the other side of the equation. That doesn't balance out. So that tells us that 1 is incorrect, and that is our right answer. And if we were to look at the other answer choices, we'd figure out that they do agree with the proportions that are created when we have similar right triangles. In question 20, we have if sine 2x plus 7 degrees equals cosine 4x minus 7 degrees, what is the value of x? Okay, going back to a point I made in a previous question, we know that the sine of an angle, sine of theta, equals the cosine of its complement. So that's 90 minus theta, right? So that's a relationship that you should know, or you can plug x, each one of the answer choices as x and figure it out that way. But this is a relationship that everyone should know. So with this relationship, we know that 2x plus 7 degrees equals 90 minus 4x minus 7 degrees. And we can distribute that negative sign in. 90 minus 4x plus 7 will equal 2x plus 7. And now it's just algebra. We subtract 7 from both sides. We can add 4x on both sides. This cancels out. We get 6x equals 90. And dividing both sides by 6, we get x equals 15. Therefore, our answer is 2 here.
All right, in this question, Sky says that the two triangles below are congruent. Margaret says that the two triangles are similar. Are Sky and Margaret both correct? And explain why. So the first thing we should do is be pretty clear about what these words mean, congruent and similar, right? So congruent means that the sides are all congruent, or the corresponding sides are congruent, and the corresponding angles are congruent. So, to say it in shorter terms, the two triangles are the same shape and the same size. Similar, okay, similar means the angles are congruent, the corresponding angles are congruent, but the corresponding sides are in some sort of proportion, right? Maybe it's scaled by 2, scaled by 3. So let's take a look here. This is a right triangle you should very quickly recognize, okay? This is a 5, 12, 13 right triangle. It's a very common triangle. Now, if we look at the second triangle here, we are looking at exactly the same thing. This will be a 12. You can use the Pythagorean Theorem to determine that last side. So Sky is definitely correct, okay? Sky is correct. They are the same triangle. It has a side of 5, 12, and 13. Margaret, okay? Margaret happens to also be correct, okay? And here's why. This angle here is congruent to this angle. The 90 degrees are self-explanatory. They're going to be the same. And then this angle here across the side of 5 is going to be the same. So the angles, we can say the angles are congruent. When we look at the sides, okay, the sides are in proportion. And what is that proportion here? That proportion is 1, right? This side maps to this side by scaling by 1. It's the same basically, right? 5 maps to 5 and 13 maps to 13. So they are both correct here. Question 22. A man was parasailing above a lake at an angle of elevation. So that's this angle right here above the horizon, this flat line. Angle of elevation of 32 degrees from a boat is modeled in the diagram below. If 129.5 meters of cable connected to the boat to the parasail, approximately how many meters above the lake was the man? So this should pop out to you immediately as a trig question, right? We have a right triangle, so that's good. So we have a right triangle, okay? We got an angle here, 32 degrees, and we have this 129.5. It's asking us how high above the lake was the man. So the lake is here. We'll call this height equals 0, right? We're looking for this here. We're looking for that distance, h, okay? So we know our trigonometry ratios here, SOHCAHTOA, okay? We're looking for this, that's opposite to 32, and we have the hypotenuse. Opposite and hypotenuse, that tells us we're going to use sine. So that tells us sine of 32, okay, should be the opposite, which is h, which is what we're looking for, over 129.5. And let's mind our units here. This is in degrees, 32 degrees. So to solve for h, all we have to do is 129.5 times the sine of 32 degrees equals the height. And from that, we find that the answer is, if we plug this into our calculator, to the nearest tenth, the answer choice is, the answer is 68.6 meters, which is choice 1. All right, this next question is a bit involved. Kirsty is testing values that would make triangle KLM a right triangle when LN is an altitude and KM is 16. Which lengths would make triangle KLM a right triangle? So what happens is we got all these answer choices. They're not all the same. You know, this one's giving us LM and KN. This gives us LM and NM. This gives us KL and KN, and this gives us LN and NM. They're kind of all over the place. The best thing probably to do here is just to go through each choice and see if they would make sense. So let's go with choice 1 first. Choice 1 says, and I'll write this in red and we'll erase it if it's wrong, LM is 13, okay, and KN is 6. So very quickly we can just see that NM is also 10, just implicitly because we know that the whole side is 16. Most important thing we're going to use here, of course, is the Pythagorean Theorem, okay? And that tells us that a squared plus b squared equals c squared. Note, very important thing to note, c is always the hypotenuse. These two are always the legs. So just note that here, hypotenuse and legs. So let's see what we could try to figure out here. We're trying to make the big triangle KLM a right triangle, right? We're trying to make this a right triangle. So we can maybe, the only thing I can really think of doing here right now is figuring out what this length has to be, okay, if we have 13 and 16 here, okay? So if we work that out, we'll get 16 squared, that's c squared, equals 13 squared plus, we'll call it x squared, okay? And that gives us 16 squared minus 13 squared, all square rooted, will give us x. I'm going to go ahead and put that in my calculator right now. That's 16 squared minus 13 squared, all square rooted, is the square root of 87. Now, that's great, okay? And we might just think, well, we just made a right triangle. However, we now have to check if this line here, LN, okay, LN, with this number, okay, is that the right leg for this small triangle KLN? And is that the right leg for the triangle NLM? Okay, that's the one adjacent to it. I'm going to color in green right now. Okay, so we can quickly do that again, another Pythagorean theorem, just to check if that works out. Okay, so for the red triangle first, the small red triangle, we have the square root of 87 squared is 87, equals 6 squared plus, we'll call it h squared, okay? And once again, we're doing this because we need to check that h is the same height for both of these triangles, otherwise these numbers do not work out, okay? So 87 equals 6 squared plus h squared, and that means h is equal to 87 minus 36, all square rooted. I'm going to go ahead and put that in my calculator. It's 87 minus 36, all square rooted. And that is the square root of 51. We can do the same exercise for the green triangle. I'll write it in green here. So 13 squared, that's the hypotenuse, equals 10 squared plus h squared. So h will equal the square root of 13 squared minus 10 squared. Okay, and if we put that in our calculator, 13 squared minus 10 squared, we get the square root of 69. This does not work out. These two numbers, okay, these two numbers had to match. Otherwise, this side, they're sharing the same side. How could it be a different length, right? We're looking at this diagram here. It can't be a different length. So choice 1 is not the answer, unfortunately, okay? So I'm going to do my work over here now for choice 2. I'm going to do it down here, okay? I'm going to erase the markings I made on the original triangle. Okay, so now we have LM is 12. Let's see if that works out. That's 12. And NM is 9. So let's see what we can kind of deduce from that. This is 9. KN has to be 7. Okay. And let's see if that works out to be a correct triangle. So we have 12, we have 16. Let's quickly find this missing side via Pythagorean Theorem. Okay. So we have again 16 squared equals, now we have 12 squared plus, we'll call it x squared, okay? And x will equal the square root, just skipping a couple steps here, 16 squared minus 12 squared. And we put that in our calculator. Okay, 16 squared minus 12 squared, we get 4 square root of 7. 4 square root of 7. Okay. So now we have that one. We now again have to check, does this height work for both of the small triangles that we've made here, right? This triangle and this triangle. So once again, I'll do it in different colors. I'll do this one in orange and this triangle on the right in green. And let's see if we get our answer. For the orange triangle, we have 4 square root of 7 squared, c squared, equals 7 squared plus h squared. H is going to be this altitude here, Ln, okay? When we solve, we get h equals 4 square root of 7 squared minus 7 squared, all of that square rooted. Let's put that in our calculator. Okay, so we have 4 square root of 7 squared minus 49, basically. That's 3 square root of 7. Okay, so let's keep that in mind. This is our h. We need this to match in the green triangle as well. So let's do it for the green triangle. 12 squared equals 9 squared plus h squared. A little bit easier numbers to work with. So that's h is the square root of 12 squared minus 9 squared. Okay, we can put that in our calculator. So that's square root of 144 minus 81, and we get 3 square root of 7. Okay, so that works out. It makes these triangles, it makes them have the right values, and we see that their heights match as well, that h, l, n. Okay, so we're pretty confident then. We can go with choice 2, and very relieved that we don't have to go through choices 3 and 4. All right, question 24. This is very similar to the question we just did. So in triangle ABC below, altitude CD is drawn to the hypotenuse AB. Explain why the big triangle ABC, so that's here, here, and here, is similar to triangle ACD. I'm going to highlight that in green. This is this small triangle over here. Okay, so first of all, we know we have right triangles. Okay, they gave it to us in the question, right triangle. So let's draw that right angle. And because we drew an altitude, this here will be a right angle as well. It's perpendicular to the hypotenuse, okay? So let's do a couple things. We know that the sum of the angles, the interior angles of a triangle is equal to 180 degrees. Let's look at the big triangle, ABC. We already have the 90 degrees here, okay? This here we're going to mark with 1 tick. Now, the missing angle is angle B here, and these have to add to 90, right? Because we already have 90 here, okay? We already have 90 from the right angle and angle ACB. So the last two angles must add up to 90. So let's just mark this with 2 ticks, okay? So basically the 1 tick plus the 2 ticks equal 90 degrees. Now let's look at angle ACD. ACD, this one over here. Okay. Again, we already have 90 here. We already have 1 tick here. Just like the big triangle, this also needs 2 ticks because these two now have to add to 90. Add to 90. Okay? So now let's just kind of redraw the triangles so we can see them a little better. I'm going to take the green triangle and draw it in a similar way to the big triangle we have here, like ABC. Okay? So here's a 90-degree angle over here. So that's vertex D. Okay? In the short side here, this is the short side, that's short side AD. This leaves us with C over here. And now, if we draw those angles in, okay, so angle A had 1 tick, angle C, or angle ACD specifically, ACD over here, had 2 ticks. If we look at the big triangle one more time, I'll draw it just so we can, it's got kind of messy, so we draw the big triangle again, ACB, or ABC. It's 2 ticks, a right angle, and 1 tick, okay? All right, so to prove these triangles are similar, okay, we can see that these 3 angles are congruent, right? These 3, this one matches to this angle, okay? Angle A matches to this angle A, and angle B matches to angle C. Now, it does suffice to prove similarity with AA, or angle, okay? So you can take your pick. We were just a bit more thorough here just to show that all 3 were. But as you can see, the 3 angles are congruent in both of these triangles, okay? And that alone will prove that we have similarity. All right, this is question 25, and we're moving into the circles section. There will be 2 questions of circles in this review. In the diagram below, circle O, GO is equal to 8, that's the radius, and the measure of angle GOJ is 60 degrees. What is the area in terms of pi of the shaded region? The easiest way to do problems like this is to understand how to set up a proportion for them, okay? So we know the area of an entire circle is pi r squared. We can actually figure that out now. That will be 64 pi because the radius is 8 and 8 squared is 64. So we have 64 pi. Now, we're going to set up a very quick proportion, okay? We're going to say, if there's 360 degrees in a circle, in a full circle, so imagine the whole thing was shaded, and I'm going to shade that right now. The whole thing was shaded, 360 degrees, the full area is 64 pi, okay? We want to know just that shaded region, okay? We know a circle has 360 degrees, and 60 degrees, that sector GOJ, has been cut out. That leaves us with 300 in the shaded portion. So I'll write shaded. Okay. We have an unknown, we'll call it x. That is the area of the shaded region. So we can cross multiply 360x equals 300 times 64 pi. Okay. Divide both sides by 360. Okay, and when we solve, we get that x equals 160 pi over 3, and that is choice 4. In circle O, diameter AB, chord BC, and radius OC are drawn, and the measure of arc BC is 108 degrees. That's this arc over here, okay? That measure of this angle. Some students wrote these formulas to find the area of this sector. I'm going to color that in red, okay? That's sector COB. Which students wrote the correct formulas? So we can set up a proportion like we did before just to get us an idea in the ballpark of what the right answer should be. So we know area equals pi r squared, and we know we're going to set up a proportion, okay? This is going to be x, like the last question, where we don't know that area of the shaded region, but we know it's 108 degrees. We know in 360 degrees, it's the full area, so that's pi r squared. R is OC, okay, OC squared. Now, the radius could also be half of AB squared, right? Because half of, let me just write here, OC is also equal to 1/2 AB, right? Because AB is the diameter, okay? When we cross multiply, we get 360x, okay, equals 108 pi OC squared. We're solving for x, so x equals 108 pi over 360 times OC squared. And we're going to hold right there. Let's quickly check the answer choices. Believe that matches with Beth's answer, okay? So Beth is already correct. We can already eliminate choices 3 and 1 because Beth is not in there. Now we have to look, is Carl correct or is Dex correct? And that helps us figure out between choices 2 and 4. So at this point, if we look, we'll look at Carl first. That's the one right after Beth. We have 3/10, okay? And if you actually try to, if you simplify 108 over 360, if you put that in your calculator, you get 0.3. That is 3/10. So that's looking good so far. It's matching Beth's answer. The pi's match. Now we have to look here, okay? 1/2 AB, that quantity squared, okay? That's important that it's that full quantity squared. We're taking the radius, that's 1/2 of AB, and squaring it. So it looks like Carl has the right answer as well. I'm going to go with choice 2. Let's just quickly look at why choice 4 is wrong, why Dex is wrong, okay? Dex has the same 108 over 360, but there's something different going on here. He has the 1/2 outside, okay, 1/2 outside of the parentheses. So that basically means we're trying to do pi r squared, but this is the diameter squared, okay? If we're squaring the diameter, that won't get us the right answer. That's not the right area. So we can be confident the answer choice is choice 2. Question 27. This puts us in our geometric properties type of questions. Triangle RST is graphed on the set of axes below. How many square units are in the area of triangle RST? Now this is a multiple choice question, so you don't have to show all your work, of course, but we can be a bit thorough. We want to know the area, which is 1/2 base times height of the triangle. Some of you might be tempted to just say, if you kind of tilt your head a little bit, that this is the base over here, and that this is the height, okay? But we want to check first that this is a right triangle, okay? So one very quick way to do that, we know that lines are perpendicular if they have negative reciprocal slopes, okay? What that means is if one of them has a slope of A, the other one has a slope of negative reciprocal, 1 over A. Let's check that real quick. In the segment RS over here, it looks like we go up 2 units over 1, up 2 units over 1, okay? So this has the slope of 2. Let's check ST, that segment ST. It looks like we go down 1 over 2, down 1 over 2. So that's negative slope equals -1 over 2. That matches, okay? So that tells us that lines segments RS and ST are perpendicular, so we can put a right angle here. Okay. Now that we know that, we simply have to find the length of the base and the length of the height as well. So length of ST, length of RS. The easiest way to do this is with the distance formula. We can review that here real quick. The distance formula is the square root, okay, of y2 minus y1 squared plus x2 minus x1 squared. Okay. Of course, you can flip these inside, or you could say the x's first and the y's first. So why don't we do that for the 2 segments we need? Let's label some points first. That'll make it easier for us. So R is -2, 1, 2, 3, 4, 5, 6, 7. This is at -2, 7. S over here is at 1, 2, 3, 4, 5. -5, 1. And point T down here is 1, 2, 3, 4, 5, 6, 7. Down 1, 2, 3, 4, 5. +7, down 5, -5. Okay, so let's find first the segment ST. Okay, that's the base, ST. So that should equal, if we do the formula here, let's call t 0.2 s 0.1. So we're going to go y2 minus y1 squared plus x2, so that's 7 minus x1, that's negative 5, so it's minus minus, squared, okay? So that will give us, that is negative 6 squared is 36, plus, this is 12 squared is 144. That gives us 36 plus 144, square root of 180. So we'll just leave it in that form. The next one we have to find is rs, okay? So that's the square root. We'll take s to be 0.2 this time of 1 minus 7 squared plus, and that's x2 is negative 5 minus minus 2 squared, okay? And that gives us 1 minus 7 is negative 6. Negative 6 squared is, again, 36. We're going to add that to negative 5 minus minus 2 are plus 2. I'll just change these signs. Plus 2. That's negative 3 squared. Negative 3 squared is 9. And that gives us the square root of 45. Okay? So all we now have to do, we now found this here is, I'll mark it in red now. This is the base. This is the height. I'm going to push my work over to here. So area equals 1/2 base times height. And when you put these numbers in your calculator, so you say 1/2 square root of 180 times the square root of 45, you will get an answer choice of 45. That's choice 3. 45 square units is our answer. Right. In this next question, they say that triangles ABC is similar to DEF. And we can kind of eyeball it and see that DEF is a scaled up version of ABC. If AB is 6 and AC is 8 as given in the diagram here, which statement will justify similarity by SAS? Just to remind ourselves, that's side, angle, side. Okay, side, angle, side. Okay, so how do we use side, angle, side? Okay, we want to prove in similarity that the sides are in proportion. Also, I'll just write prop here, proportion, and that the angle, okay, is congruent. So they already gave us two sides, so we can guess that it's going to tell us, or the answer choices will be surrounding this side here, because that's the corresponding side. It'll be about this angle here, and it'll be about this side here. That's side, angle, side, okay? So let's see what the proportion is of the angles. We can first, actually, before we do that, let's just see if they're congruent. We want A and D to be congruent based on SAS. They have to be in this specific order here, right? So we already know it has to be choices 1 or 2. We can eliminate 3 and 4. Okay, let's look at the proportion now. Okay, so if we chose, let's just entertain option A or option 1. Let's see if that's the correct one. It's saying, is DEF, we have that as 9 and 12, is that in some sort of proportion? So let's take a look. Let's compare it to ABC. So 6 mapped to 9. Okay, so I'm going to mark that here. So this 6 mapped to 9. Okay, and AC was 8. DF was 12. Is this proportion correct, right? Because that tells us we scaled it up by the same number. 6 became 9, 8 became 12. And when we solve this, or when we simplify this, okay, we get 2/3 equals 2/3. So we don't really have to look at choice 2 anymore. We're pretty confident that choice 1 is the answer. Okay, we can set up this proportion, by the way, another way. We can say, we can do it like this, that 6 and 8 were of the original triangle. That's AB, this is AB and AC, okay? And then that 6 mapped to the 9 in DE, and mapped to the AC mapped to the 12 in DF, okay? So they're using the same numbers. You could just set up the proportion differently. you will get here 3/4 equals 3/4. So it's the same thing. Here, I'm just going to be thorough and write which side I was referring to. So this was AB over DE. So D. And then this here was AC over DF. Question 29. Using a compass and straight edge, construct and label triangle ABC, the image of ABC after a dilation, with a scale factor of 2 and centered at B, and leave all construction marks. Okay? So we're going to scale it by 2. That's a dilation, right? Scaling it by 2 and centered at B. When something is centered at something, it doesn't move from there. So we know this point will stay. Okay? Now here's what we're going to do. I can't show with a compass really here. So I'll draw in a different color. I'll draw it in orange so we can see what we would do with our compass. Okay? So if we took our compass and we're scaling everything by 2, that means doubling the length, right? So if you take your compass and do this, open it to such an angle that it spans AB, and we now shift that compass over, okay, and go like this, we can quickly mark, with this being the center, you can kind of mark a little arc over here, just to show that we've kind of doubled the length, okay? If you now take a straight edge and go through this way, you'll find the intersection point here, and that's that's point A dilated with a factor of 2. Okay, so we know now this is point A prime. We can do a similar exercise here with BC. Okay, so if we take a compass, just to get that length measurement, BC, shift the compass over so now that the needle is on C, okay, like this, and we draw a little arc. Okay, we take our straight edge and we go through BC and just keep extending that line. Here's our next point, C prime. And like we said before, B does not move because the scaling is centered at B. So that's B prime as well. It's the same point. If we connect the triangle now, maybe I should do this in green or some other color. Okay. This triangle here is our scaled up triangle by a factor of 2 and centered at B. And we left our construction marks, which were from the compass and from the straight edge, okay? So now we have to describe the relationship between lengths AC and A prime C prime. Okay, so that's this here, I'll mark it with 2 ticks, and this here with 1 tick. Okay, so we know that this triangle is similar. And how do we know that? Or these two triangles are similar. They share an angle here, and we just scaled up this side by 2 times 2, and this side by 2. Okay, so by side angle side, we know the proportions that the sides went up by are congruent, are the same. Okay, and the angle that they share, an angle B or B prime, however you want to call it, is the same. So these two triangles are similar. So by that same property, so we could say SAS similarity. Okay, because we can prove that SAS, by SAS, that these two triangles are similar, that means that final side AC, okay, must have also scaled or dilated by a factor of 2. Okay, so it's basically the length AC double 2AC equals A prime C prime. Okay, question 30. Which equation represents a line that is perpendicular to the line represented by 2x minus y equals 7? Okay, so let's rewrite this in a form we're more familiar with, in a y equals mx plus b form. Okay, so we have 2x minus y equals 7. Let's add y to both sides, and let's subtract 7 from both sides. Okay, just do it all in one step. So we have 2x minus 7 equals y, because this cancels with this. So it's y equals mx plus b. Now, very important to know is when something is perpendicular, we sort of went over this in a previous question, perpendicular, the slopes of the line, slopes of lines are negative reciprocals. Okay, again, what that means is we have a line, let's say, that has a slope of 2, as we have here, right over here. We need the perpendicular line, a line that's perpendicular to that original line, to have a slope of negative 1/2, okay? So we'll just quickly graph this. We don't need to, okay? It doesn't have to be an exact answer because there's actually infinite amount of answers, okay? -7's over here, and we'll say the line looks something like this, okay? Well, a line that's perpendicular could look like this. That's perpendicular. It could look like this. Okay, could look like this. So there's many lines. You can just draw all these lines throughout the entire original line. Right? I could keep going with all these blue lines. These are all perpendicular to the original line. The most important thing is that these all share is that they have a slope of negative 1/2, because that's the negative reciprocal of the slope of this red line here, which had a slope of 2. So if we look at the answer choices, it's very clear which one's the answer. We don't really have to care about the +6, okay? Let's just say here's the +6. It doesn't really matter. The only line that will be perpendicular to the original one will have a slope of negative 1/2. That is only satisfied by choice 1.
Quadrilateral NATS has coordinates n, -4, -3, a, 1, 2, t, 8, 1, and s, 3, -4. Prove quadrilateral Gnats is a rhombus. Let's quickly, before we get into the question itself, let's quickly draw this out on the graph provided. So n is at -4, -3, that's right here. A is at 1, 2, that's right here. T is 8, 1, that's right here. And S is at 3, -4, right here. N, A, T, and S. So let's connect these lines. Alrighty, let's get started. So to prove a quadrilateral is a rhombus, we must first prove that all these, the opposite sides are parallel, because it must be a parallelogram first, right? So opposite sides are parallel. And second, you have to prove that it's a rhombus. So this proves that it's a parallelogram, right? I'll put that in parentheses. This proves that it's a parallelogram. But more specifically, it's a rhombus. So rhombuses have a property of their diagonals being perpendicular to one another. In this case, that would be, I'm going to mark it in green here. I'll read this and this. They would have to be perpendicular to one another. All right, let's start with the parallelogram portion. So to have opposite sides parallel, that means that this slope of AN has to be equal to the slope of ST, and the slope of AT must equal the slope of NS. We can see here, by looking at the graph, we have ST, it seems like it has a slope of 1. AN has the same exact slope, it looks like. And segment AT has a slope of, you have a rise of -1 and a run of 1, 2, 3, 4, 5, 6, 7. So this is -1/7. I'm doing rise over run, same thing with NS, -1 over 1, 2, 3, 4, 5, 6, 7. So this is indeed a parallelogram. That's what we just proved. In addition, we must have the diagonals be perpendicular to one another. Now, what does that mean? That means that their slopes have to be, let me change color. Their slopes, let me change to green. Their slopes have to be negative reciprocals of one another. All right. So AS, we have minus 1, 2, 3, 4, 5, 6 over 1, 2. So this slope is minus 6, and then run is 2, which simplifies to negative 3. And for this diagonal, we've got a rise of, looks like 1, 2, 3, 4, and a run of looks like 12. And that simplifies to 1/3. And we can see that, let's bring these values here so it's easier. We have a negative 3 and we have a positive 1/3. And now these are indeed negative reciprocals of one another. So it does satisfy that this condition that the diagonals must be perpendicular to one another. And thus, quadrilateral Gnats is indeed a rhombus. The line negative 3x plus 4y equals 8 is transformed by a dilation centered at the origin. Which linear equation could represent its image? So let's reorder this equation into its y equals mx plus b form, just for our sake. So we got negative 3x plus 4y equals 8. We can add 3x on both sides and get 4y equals 3x plus 8, and divide both sides by 4 to get y equals 3/4 x plus 2. So now let's think, what happens when a line is dilated, right? So let's do a rough graph of this. We have 3/4 x, so we know that it's sloping, it has a positive slope, and it intersects the y-axis at y equals 2 here. Okay. So when we dilate a line about the origin, centered at the origin, all it does is it just shifts it outwards from the origin to an arbitrary point in this case. So you can see that in going from the original line to this new green line, that our slope is conserved, right? So let's just look for an answer where our slope is conserved. We can see that, oh, answer choice 2, our slope is the same, right? So that must be our answer. These other slopes do not agree. A large water basin is in the shape of a right cylinder. The inside of the basin has a diameter of 8 1/4 feet and a height of 3 feet. Determine and state to the nearest cubic foot the number of cubic feet of water that it will take to fill the basin to a level of 1/2 foot from the top. All right, let's draw this out. We have a right cylinder. And we have a height here of 3 feet. We also have a diameter of 8 1/4 feet, 8.25. Now it's asking us how much water will it take to fill it 1/2 foot from the top. So that would be here, right? Right here. I'll just draw it here and say that this is, we can do a 3 feet minus a 1/2 foot to get 2.5 feet. So basically, all this question is asking us is, what is the volume of this? Let me reshade that. What is the volume of the water that fills this portion of the basin, right? So we can ignore 3 feet now and just use our values 8 and 1/4 feet and 2.5 feet to calculate the volume of the cylinder. So volume of a cylinder is pi r squared h. And 2.5 feet is our height. R is 8.25 divided by 2. 8.25 divided by 2 is 4.125. And all we have to do is plug in. And we can put these values in our calculator to get 133.64. Now, these are in cubic feet. And it tells us to state this answer in the nearest cubic foot. So we round this up to 134 cubic feet. And that's our final answer. A vendor is using an 8 by 8 foot tent for a craft fair. The legs of the tent are 9 feet tall, and the top forms a square pyramid with a height of 3 feet. What is the volume in cubic feet of the space the tent occupies? All right, so let's break this down. What is the volume that this tent occupies? Well, we can split it up into this square pyramid portion and this rectangular prism portion on the bottom. So with a rectangular prism, we know that the volume, in this case, is length, width, height. Length times width times height. So that's just 8 times 8 times 9. That gives you 576 cubic feet. Now the volume up here, the volume of a square pyramid is 1/3 length times width times height, right? With length and width representing the base. So we know that this measurement here is also 8 feet, and this measurement is also 8 feet. So this in turn gives us 1/3, 8 times 8, times our height here of 3 feet. So these 3's cancel out, and that gives us a square pyramid volume of 64 cubic feet. Now we can just add both of these together to get a total of 640 cubic feet. And that's our final answer. So this question starts our topic of modeling. So a child's tent can be modeled as a pyramid with a square base whose sides measure 60 inches and whose height measures 84 inches. What is the volume of the tent to the nearest cubic foot? So it's telling us that the child's tent will just look like this. A square pyramid. We know that the volume of a square pyramid, which is what it's asking us, is 1/3 base times height. Base being our length and width. We know that the base is just 60 times 60. So that's 1/3 60 times 60. And we also have a height of 84. Multiplying this out, we get 100,800 cubic inches. Now we run into a problem here. None of the answer choices reflect that, right? Because it's asking for cubic feet. Meanwhile, we have cubic inches. So I see 2 ways to go about amending this. We can either convert each one of these inches values that we put into our original equation and divide each one of them by 12 to get our feet value. But we can also try to convert our final value here into feet cubed. cubic feet. So we can do 100,800 cubic inches. And we can multiply that. We know we're trying to get rid of that inches cubed. So we're going to put inches down here quickly. And we know that 12 inches go into 1 foot. But we have to do this a total of 3 times because we want to convert from cubic inches to cubic feet. So there's a cubed here. So doing this math out, we get a value of 58.3 repeating. And it's telling us to round to the nearest cubic foot, so we just round this down to 58 cubic feet. And that's our final answer. Shay has recently begun kickboxing and purchased training equipment as modeled in the diagram below. The total weight of the bag, pole, and unfilled base is 270 pounds. The cylindrical base is 18 inches tall with a diameter of 20 inches. The dry sand used to fill the base weighs 95.46 pounds per cubic foot. The question asks, to the nearest pound, determine and state the total weight of the training equipment if the base is filled to 85% of its capacity. So if we're going to do 85% of the base filled, right, let's first find the volume of the base. So the volume of the base is the right cylinder. So its volume is pi r squared h. In this case, we have a diameter of 20 inches. So let's divide that in 2. So we know that its radius is 10 inches. Let's plug that in. We have everything we need. Pi 10 squared times h, which is 18 inches. That gives us a value of 1800 pi. All right. So now we're being told that this base is only filled to 85% of its capacity. So let's multiply this 1800 pi value, by 0.85, which is equivalent to 85%. That gives us a value of 4806.63675. So now that we have the volume, this is in inches, cubic inches, right? And again, the information given to us is that to find the weight of this, we have 95.46 pounds per cubic foot. We calculated this in cubic inches. Let's convert it. We have 4806.63675 inches cubed. And let's try to cancel that out. We know that there's 12 inches in 1 foot, and we can cube this value because it's a cubic, right? So that makes, for dimensional analysis wise, that makes the inches cubed cancel out so that we're left with feet cubed. So doing this, we get this volume is 2.7816 cubic feet. Now that we have cubic feet, we can take this value, I'll bring it up here, 2.7816 feet cubed, multiply that by our 95.46 pounds per cubic foot, and that gives us a value of 265.533. So now we're not done yet. This is only this pounds that we got here is only the weight of the base, right? It's only the weight of this portion. We have to add it to the dry mass, right? The mass without anything filled. So it's given to us the unfilled, everything with an unfilled base is 270 pounds. So we must do 270 pounds plus the value that we got here. And with that, we get a final answer of 535.533. And remember, it tells us to do it to the nearest pound down here. So let's make sure to do that. Because it's 0.533, we round up. So we get 536 pounds as our final answer. The greenhouse pictured below can be modeled as a rectangular prism with a half cylinder on top. The rectangular prism is 20 feet wide, 12 feet high, and 45 feet long. The half cylinder has a diameter of 20 feet. The question asks, to the nearest cubic foot, what is the volume of the greenhouse? Well, they've broken it up fairly easily for us at this point already. They said that the bottom is a rectangular prism, and the top is a half cylinder. So let's first calculate the rectangular prism as it's the easiest. We know that the volume of a rectangular prism is length times width times height. In this case, we have a height of 12, we have a width of 20, and we have a length of 45. Now that gives us a volume of 10,800. And this is in cubic feet. For the top, we just have to make sure that we're taking half the volume of a right cylinder. So we have 1/2 the volume equals 1/2 pi r squared h. In this case, r is half of 20 feet, which is 10 feet, is our radius. And our height would be this 45 feet value. So this turns into 1/2 pi. I'm just going to do 10 squared, which is 100, times h, which is 45 feet. So doing this, calculating, putting it in our calculator, we get 0.5 times pi times 100 times 45. We get 7068.583 cubic feet. And now it's telling us to find the volume of the greenhouse, so we have to add both of these together. To get 17,868.58. And we can see that if we have to do it to the nearest cubic foot, so we're rounding this value up to 17,869. And which answer reflects that? We have answer choice 1. A rectangular in-ground pool is modeled by the prism below. The inside of the pool is 16 feet wide and 35 feet long. The pool has a shallow end and a deep end with a sloped floor connecting the two ends. Without water, the shallow end is 9 feet long and 4.5 feet deep, and the deep end of the pool is 12.5 feet long. If the sloped floor is an angle of depression of 16.5 degrees, what is the depth of the pool at the deep end to the nearest tenth of a foot? So what it's trying to tell us to find is this value over here. So looking at the sloped portion of the pool, we can see that it's a simple trigonometry problem. We can isolate this, and it's just a triangle, right? A right triangle. Let's do some trigonometry. We know that this leg, because we're given 9 feet here and 12.5 feet here, with a total length of the pool of 35 feet, we can find out the length of this leg by doing 35 feet, all right, up here, 35 feet minus 9 feet minus 12.5 feet. To get 13.5 feet. So we know this leg is 13.5. Now we're trying to find out how much deeper it goes, right? So we're trying to find an opposite side, we're given an adjacent side, and we're given a degree. So this is a tangent, right? So SOHCAHTOA, we have tangent of theta equals opposite over adjacent. We can plug in our values here. Make sure when you input in your calculator, this is in degrees. equals opposite over adjacent, which is 13.5. We can multiply 13.5 on both sides and just throw this in our calculator. In this case, we get a value of 3.9988 feet. So we know that from the shallow end, it goes approximately 4 feet deeper, and then that's the deep end. So we add this value to our original depth of 4.5 feet. To get 8.4988. And now this is our final depth. It tells us to round to the nearest tenth of a foot, so this answer is 8.5 feet. We have a second portion of the question, and it tells us to find the volume inside the pool to the nearest cubic foot. All right. So there's a few ways to go about doing this. We can take, let's say, we can divide this pool up into a few more easily palatable rectangular prisms, right? But the way I choose to do it this time around, let me erase this, is to take this area here and subtract this trapezoid portion from it. Let me draw that out over here on the side. So we have a cross section of our pool, right? I'm not going to concern myself with this 16 feet depth yet, right? I'm just going to look at this cross-sectional area, and we know that it looks something like this. And this trapezoid is the trapezoid I'm going to subtract out from this rectangle. So we know that we have a total depth of 8.4988 feet. We have a total length of the pool of 35 feet. So I can just multiply those two out and get 297.46 squared feet. All right, and I want to subtract the area of this trapezoid. So what is the area of a trapezoid? The area of a trapezoid is 1/2 times the length of base 1 plus the length of base 2 in parentheses times the height. Now we're given all this information. We know that, let me cut this here. We know that this portion is 9 feet, and we know from our previous portion of the question that this is 13.5 feet. So we know we know the lengths of both bases in this case, right? So we can do 1/2 times 9 feet plus, so that 9 plus 13.5 gives us our second base. 9 plus 13.5, that gives us 22.5 as our second base, times our height, which we also got from the previous question, and we know that to be that value there, 3.9988. We can multiply this out, and we get a value of this trapezoid. The area of the trapezoid is 62.982 squared feet. So let's subtract this from our total area of the rectangle. And we get a value of 234.478 squared feet. So now that we have this cross-sectional area, this is the cross-sectional area. I'm going to mark it in yellow. This cross-sectional area, we have this area now. We can now multiply that by 16 feet. So we take this value and we multiply it by 16 feet. And we get a value of 3,751.655. And this is in units of cubic feet. And it tells us to round to the nearest cubic foot, so we can round that up to 3,752 cubic feet. And that is our final answer. In question 39, we have a fabricator is hired to make a 27-foot long solid metal railing for the stairs at the local library. The railing is modeled by the diagram below. The railing is 2.5 inches high and 2.5 inches wide and is comprised of a rectangular prism and half a cylinder. How much metal to the nearest cubic inch will the railing contain? So because this question is asking for cubic inches, let's convert 27 feet to inches. We can simply multiply 27 feet by 12 inches per foot to get 324 inches here. All right, so let's calculate. Let's separate this out into two portions. We can calculate the rectangular prism portion first, then the half cylinder portion up top. All right, so rectangular prism, we have the volume equals length times width times height. In this case, we have a length of 2.5. Oh, we have a width of 2.5. We have a length of 324 inches. And we have a height of 1.25 inches. You see we're dividing it by 2 here because we know that with a cylinder that this length here is 1.25, meaning that because it's a cylinder, it's a circle, right? That this length is also 1.25, which is half of 2.5. So doing this, we get 1012.5 over here, and that's in cubic inches. Now let's try to find the volume of that half cylinder up there. You know the volume of a cylinder is pi r squared h, but we know we're going to have the volume, right? Because it's a half cylinder. And we have our r over here, 1.25. We have our height, which is our 324. So let's just plug that in. So we get 1/2 times r squared, 1.25 squared, times h, 324. And we get, oh, I apologize, we had to put a pi in here as well. We get 795.215, and that's in cubic inches as well. Now let's just add both of these values up together. To get 1,807.715. It tells us to round to the nearest cubic inch, so we round this up to 1,808 cubic inches, and that gives us answer choice 3. A candle maker uses a mold to make candles like the one shown below. The height of the candle is 13 centimeters, and the circumference of the candle at its widest measure is 31.416 centimeters. Use modeling to approximate how much wax to the nearest cubic centimeter is needed to make this candle. Justify your answer. All right, so let's convince ourselves that this candle is shaped like a cone, right? So we have this circumference of this base right here. The circumference is 31.416 centimeters. It tells us the height, which is 13 centimeters. And all it's asking us to do by saying how much wax is, what's the volume of this cone, right? So let's try to find the volume of a cone. That's looking in your reference sheet. We have 1/3 pi r squared h. So to find r, we're currently given our circumference, right? So how do we get from circumference to diameter and radius? Well, circumference, all circumference is pi d, right? Equals pi d. But diameter is equal to 2r, so we can just do 2 pi r here, right? So 31.416 centimeters, divide that by 2, and divide by 2 pi, sorry. And that gives us a value of approximately 5. So we get r equals 5.00001. All right, so we can simply just plug that in there. And we already have our height, we can plug that in here. So doing that, we get 1/3 pi 5.00001 squared times 13. And multiplying that out, we get 340.340. And that's in units of cubic centimeters. It tells us to round to the nearest cubic centimeter, so we can round this down to just 340 cubic centimeters as our final answer. So this concludes our geometry review. We would like to thank you guys for listening, and we wish you the best of luck on your exam.